which would be plus a cosine of t times j. And that's multiplied by delta t, and t is evaluated at the sample point ti star. Now, what's the gradient of x squared y? That's easily written. Gradient of x squared y is 2xyi plus x squared j. At the point ti, with this parameterization, we get xy is just cosine t sine t, 2 cosine t sine t times I, where t is evaluated again at the sample point ti star, plus x squared j, which would be cosine squared of ti star times j. So that del f, well, del of x squared y dot delta si equals dot product of the delta si vector with this vector. So we're going to have negative 2 cosine t sine squared of t, both evaluated again at ti star. And then it's going to be plus the cosine times the cosine squared, so that's going to be plus the cosine squared of ti star, and all that times the delta t factor. Now, the sum of our expression, the sum of our contributions from the various increments, and I'm not going to write out this expression, but that sum approaches the integral of negative 2 cosine t sine squared t plus cosine, let's make sure we've got that, we had a cosine squared here and we had a cosine here, which should have given us a cosine cubed. Okay, so that's going to be cosine cubed of t dt, the integral going from 0 to 2 pi. Now I'm running out of room, and to keep this brief, we saw a very similar integral in a very recent clip. With u substitutions, we're going to find that every term in the antiderivative here, every non-constant term in our antiderivative, is going to be an odd power of the sine of t. So it's going to be odd powers of sine of t evaluated at 2 pi and 0. And that is going to be 0, and you can verify that, but simply any power of sine of t evaluated at 0, 2 pi is going to give you the same result, so that when we subtract the result, our antiderivative at 2 pi, when we subtract our value of the antiderivative at 0 from the antiderivative at 2 pi, we're going to get the same two values. We'll be subtracting equal values, and we're going to get 0. Based on these results, we're going to make a conjecture, and then we're going to prove that it's so. The conjecture is that the closed line integral of any function which is a gradient function dot with the increment vector ds is going to be 0. again, this function is a gradient. This function is a gradient. Both integrals are 0. This function is not a gradient. The integral is not 0. Here we integrated an actual gradient, and though we didn't complete the very last step, it's easy to see from what we did that the integral is going to be 0. Now, we don't know how far this conjecture goes, but let's just look at what happens if we integrate something like a gradient function dotted with the ds vector. In other words, we do a line integral of the gradient function around a closed curve.